The magnetic force results from the interaction between a moving charged point particle or current and a magnetic field. This is the equation for the magnetic force acting on a charged point particle. It depends upon the net electric charge of the point particle, the velocity of the point particle, and the magnetic field through which the particle is moving. This figure shows a positively charged point particle moving in the presence of a uniform magnetic field. The direction of the magnetic force acting on this point particle is found using the equation shown. We see from the right-hand rule that the cross product of the velocity v and the magnetic field B points downward. Since the net electric charge of the point particle is positive, the direction of the magnetic force is thus also downwards. This magnetic force will result in the centripetal acceleration necessary for the particle to undergo uniform circular motion. When a charged particle is moving in the presence of both an electric field and a magnetic field, it will feel a separate force from its interactions with each of those fields. The net force experienced by a charged particle moving through both a magnetic and an electric field is called the Lorentz force. Consider the positively charged point particle moving through the perpendicular uniform electric and magnetic fields shown in the figure. The Lorentz force acting on this point particle will have an electric and magnetic component. These two forces point in opposite directions. We can use the equation for the Lorentz force to determine the condition when the net force is zero. In other words, we can determine the condition so that the magnitude of the magnetic force is equal to the magnitude of the electric force. This calculation shows that the condition for no force on the point particle corresponds to the condition where the magnitude of the electric field is equal to the product of the magnitude of the magnetic field and the speed of the particle. This is the equation for the infinitesimal bit of magnetic force acting on an infinitesimal bit of a current carrying wire in the presence of an external magnetic field. It depends upon the current in the wire, the magnetic field, and the associated infinitesimal bit of length of the wire. The direction of the vector associated with this infinitesimal bit of length is the same as the direction of the current. The total magnetic force acting on the wire is found by integrating the infinitesimal bits of magnetic force acting on each infinitesimal bit of length of the wire. Let's use this equation to determine the magnetic force acting on this current carrying wire. We know from the cross product in this equation that the direction of the magnetic force is upwards. Let's define the y-axis to be the same as the direction of the current. The vector ds is thus dy y hat. The magnetic field points into the page and thus can be expressed as b times negative x hat. Substitution of these values into the equation for the magnetic force acting on the wire gives us the following integral. Solving for the cross product gives us a straightforward integral along the length of the wire. The magnitude of the magnetic force is thus the product of the current in the wire, the magnitude of the magnetic field, and the length of the wire. The direction of the magnetic force is upwards, as expected.